The Machine Learning-Based Analytics for Automated Rover Systems, or MAARS, was a JPL Strategic Research and Technology Development task which started in 2017. The goal of the task was to make future rovers safer and more productive through novel autonomy capabilities running on high-performance spacecraft computing, or HPSC, a next-generation onboard computer. As the grand finale of the successful 3-year project, we performed a field demonstration in the Arroyo Seco, a dry riverbed next to JPL, with the Athena rover. The demo showcased 5 capabilities which were enabled by our new software, named after your favorite Star Trek characters: Spock, Scotty, Sulu, Rand, Uhura, and V'ger. The first capability was long-range autonomous driving at 2 times the speed of the Perseverance rover. In the demo, the Athena rover autonomously drove over 500 meters from the northeast to southwest corner of the Arroyo. The autonomous drive was achieved by commanding a goal to the RAND strategic planner, which generated waypoints on the fly to an onboard, terrain-aware local navigation stack implemented using ROS. The second capability was terrain-aware navigation. Unlike existing MAARS rovers that only use geometric information to detect obstacles, humans also use textural information to drive on Earth and Mars. Likewise, our algorithms allow rovers to use both geometric and textural information to tell terrain types, assess mobility risks such as sand traps, predict slip, sinkage, and driving energy. In the demo, Sulu interpreted the images and Spock classified the terrain into 7 categories: sand, gravel, big rock, vegetation, debris, artifacts, and biotic substances, which are typically the waste product of a quadruped lifeform that is commonly seen in the Arroyo carrying a biped, potentially intelligent species. V'ger used Spock's terrain classification and the elevation map to create a local predicted energy cost map for path planning. We tuned the cost so that Athena drives preferentially on sand to reduce the localization error due to vibration. The third capability that we demonstrated was onboard resource-aware strategic planning. It is not always optimal to drive the shortest route. Instead, making a detour to drive on a hard surface which requires less energy, or taking a nap on a sun-facing slope to charge batteries can allow the rovers to drive further. Our onboard algorithm allows rovers to consider such complex constraints and cost functions and quickly re-optimize the plan when the rover state deviates from the current plan. In the demo, we pre-computed several path options, and the onboard RAND executive produced waypoints for the local path planner by reacting to the current state of the rover. The fourth capability was drive-by science. Modern spacecraft instruments can produce a substantially greater volume of data than can be downlinked. Because of that, a future rover that would drive many kilometers every day could pass by a green monster without it being noticed. In fact, there were a number of serendipitous discoveries in the past Mars rover missions, such as the evidence of neutral water found by Opportunity and meteorites found by Curiosity, which might have been left unnoticed. We addressed this issue through onboard content-based search. The rover would continuously scan the terrain and store and index all the data in an onboard database. The ground scientists would then send queries to the rover to search the data and selectively downlink the data that is relevant to their interests. In the demo, Sulu produced feature vectors that represent every onboard image, and Scotty generated natural language captions of the images. The images, feature vectors, and captions were sent to an online database on which the remote viewers performed search by keywords or image similarity using our web interface, Uhura. The fifth and the final capability was the onboard execution of these algorithms on HPSC analog computers. Athena used 2 Jetson TX2s as the onboard computer cluster, which have 8 ARM V8 cores. This configuration is comparable to the HPSC and the Snapdragon 855, each of which have 8 ARM-V8 cores. The TX2 also has a GPU that is similar to the one on the Snapdragon. Our field tests were substantially impacted by the lab shutdowns due to COVID-19 and the Bobcat fire. Despite the highly unfavorable situation, we successfully completed a semi-live virtual demo on September 18, 2020, completing the delivery of all the stated goals of the MAARS task. Over the 3 years, the task produced 2 journal papers, 1 book chapter, and 3 conference papers. The terrain classifier Spock, which was partially funded by this task, won JPL's Software of the Year award in 2020 and an honorable mention in NASA Software of the Year competition. The improvements we made to Spock in this task were infused into MSL's ground operations system. Trained by more than 100,000 labels generated by citizen scientists, it achieved 91% overall accuracy on Curiosity's NavCam dataset. These innovations were made possible by many talented technologists and scientists across the sections, as well as highly capable student interns. We thank JPL's OCSCT and the 4X and 6X program offices for their financial support over the 3 years.